Am I audible? Can some of you confirm?
Yes, sir.
Okay. So let us take the first question for today. It's from Control Systems, Gate 2020, Instrumentation, Technical Question 55. The loop transfer function of a negative feedback system, G of S into H of S, is 2 into S plus 1 upon S square. The phase margin of the system is. So this loop transfer function is given and we have to find the phase margin. So let us see how will we solve this question. So the phase margin is defined as the amount of change in open loop phase needed to make the closed loop system unstable. So what I mean by this statement is, suppose you have a Bode plot of a system on the left, assume this blue line, and this is the phase of that Bode plot. So when this magnitude plot of that transfer function, the point at which it crosses 0 dB, it should have a positive phase margin. What I mean by positive phase margin, that the phase should be above the minus 180 degree line. Basically it should be uh, above minus 180 degree. In this, right, the phase margin is negative because the 0 dB line where it is crossing, the phase of the system is beyond minus 180 degrees. Okay, so it contributes to negative phase margin. Basically phase margin is always looked at with respect to minus 180 degrees. So you have to ensure that it is between 0 to minus 180 degrees. Say example, assume it is minus 135 degrees here. So it is a stable system due, due to it having a positive phase margin as the condition for the stability. So let us see how will we solve this question. So basically we have to check it at 0 dB line. 0 dB corresponds to magnitude of 1. So when we take substitute S equal to j omega and equate this magnitude as 1, we'll get this expression. Then we'll just rearrange these terms and substitute omega square as say some constant k and solve this quadratic equation. So we get these two solutions. Omega square is equal to 4.828 and omega square is equal to minus 0.8284. So we'll disregard this negative term and we'll take this 4.828 omega equal to 2.197, and from this transfer function we'll calculate the phase angle also. Minus s square will contribute to 90 degree twice in the negative side, so minus 180 plus tan inverse omega. Why tan inverse omega is s equal to j omega and this is 1, so omega by 1 is omega only. So when we substitute omega equal to 2.197 in this transfer function, we get minus 180 plus 65.52, that is the phase of minus 114.47, approximately minus 115 degrees. Now phase margin is with respect to minus 180 degree line. So again, if we look at it directly, then minus 180 plus this angle, so phase margin is 65.52 degrees. So this is the answer to this question. The only careful thing you need to do here is this 2.197 is put in radians here. Okay, so just be careful. Tan inverse omega. So whenever this tan and everything is there in this equation, make sure this is in radians and everything. Here, although it doesn't matter whether it is in radians because it's tan inverse, but when you're calculating tan of some omega, so that time in control system, make sure it is in radians. Okay. So the answer to this question is 65.52 degrees, the phase margin. Yeah. Any doubts?
No, sir.
Okay. Let's take next question from control systems only. So gate 2020 from instrumentation, technical question 50. So consider the following state variable equations. X1 dot of t is equal to x2t, x2 dot of t is equal to minus 6 x1t minus 5 x2t. The initial conditions are x1 of 0 is equal to 0, x2 of 0 is equal to 1. So at t equal to 1 second, the value of x2 of 1 rounded up to 2 decimal places is. Okay. So all these things are given, the initial conditions and the differential equation format. So when x1 of 0 and x2 of 0 and some differential equations are given, you can take a hint that you can approach these questions with a Laplace domain approach instead of staying in the time domain. So let us see how will we solve this question. So let us look at this first equation. These three equations are from the question only. I have just replicated them. So let us look at the first equation. X1 dot of t is equal to x2t. And by taking Laplace transforms, so Laplace of this differential operator dot basically is dx1 by dt. So s x capital X1 of s minus x1 of 0. This is the Laplace domain translation of this time to Laplace domain is equal to, here it will be only x2 of s, where capital notation signifies Laplace domain and small notation is in time domain. Now as x1 of 0 is 0, we'll directly write sx1 of s is equal to x2 of s. Now let us look at the second equation, which is the blue one. So x2 dot of t is equal to minus 6x1 minus 5x2. And already in the previous slide we established that sx1 is equal to x2. So by taking again Laplace, sx2 of s minus x2 of 1, x2 of 0, that is equal to 1. So we substitute this, and then we substitute this red equation in that, and we get everything in terms of x2 because we wanted x2 at 1 seconds. So at the end of the day we want x2 of t in time domain. So we are solving for x2 of s and then we'll take inverse Laplace transform. So by rearranging terms, we get that x2 of s is equal to s upon s square plus 5s plus 6. So by taking factors and we'll do partial fractions. So x2 of s is equal to minus 2 s plus 2 plus 3 upon s plus 3. So this is the time domain equation, minus 2 e raised to minus 2t plus 3 e raised to minus 3t. Okay, so these are the steps. I'll summarize here. Partial fractions, then inverse Laplace transform of these two equations, and when you substitute x2 of 1, which is asked in the question, so minus 2 e raised to minus 2 plus 3 e raised to minus 3 is minus 0.121. Okay, so this is the answer to this question for x2 of 1. Okay, so any doubts in this question?
No, sir.
Okay, so let us look at the last question for today. So it is GATE 2020. It is from circuits. So GATE 2020 instrumentations, technical question 51. So assume the diodes in the circuits are ideal. The current Ix flowing through the 3 kilo ohm resistor in milliamperes. This is important. Rounded off to 1 decimal place is. So this circuit is given to you, and how will you proceed with finding the current through 3 kilo ohm resistor? So let us look at the right half of the circuit first. So you don't know which diode will conduct, but you can always start with an assumption. So assume let's say the 5 volt side of diode will start conducting. Assume this starts conducting initially. So, and this diode is given as ideal. So this will have no drop. Okay. So this 5 volt will get shorted and 5 volt will come here. Okay. So when this 5 volt will come here, the drop across anode to cathode of this diode again will be positive. So 10 volt will also get shorted. So 10 volt will be trying to have its potential here. And similarly, if either 5 or 10 volt comes here, the anode to cathode of this 15 volt diode will also try to conduct and impose a 15 volt here. So the highest voltage which is coming here is the 15 volt, no matter whichever voltage of the bottom tries to conduct in the bottom. So if a 15 volt source is imposing its potential here, the anode to cathode voltage of remaining two diodes in the bottom are negative. So this too will be reverse biased if a 15 volt source is available here. So 10 minus 15 will be minus 5. It is a reverse bias for an ideal diode, and 5 minus 15 will be minus 10 for a reverse biased condition for an ideal diode. So these two diodes won't conduct if a 15 volt source is available here. So this side of the circuit is sorted out. So here 15 volt will come. Now here if you look at, assume, start off with one thing. You assume 15 volt is here, and you see individually. Let's start with 6 volt first. So if 15 and the 6 volt, you can always apply superposition theorem later to calculate the current by taking individually. But let us start with 6 volts first. So 15 and 6 volt, and assuming this diode will conduct. So you just try to calculate the potential at this point. Okay, at this point. So if you happen to calculate the potential at this point, and if the potential at this point for the 6 volt combination, if it comes below 12 volt, this diode is never going to conduct because of reverse bias condition, because the anode to cathode voltage will be negative. It will be reverse bias. So let us see, like this potential, if you calculate it, it comes out to be roughly 9.6 or something. I have not shown it here, but that itself, assumption, when you proceeded that only 6 volt will conduct, that itself will validate that this 12 volt side of the circuit won't conduct. So only this 15 volt to the 6 volts will be the conduction path, and the answer will be 15 minus 6 upon 5k, that is 3k plus 2k, that is 1.8 into 10 raised to minus 3 ampere. The answer is asked in milliampere, so answer will be 1.8 of this question. So any doubts in this question?
No, sir.
Okay. Yeah. So I would like to conclude this session, and this is the last lecture for this run of the course. You all the best for the GATE exam, because this is the last week. 31st is the last date for the live sessions. So maybe it will start later in the April or something again. So thank you guys for joining, and all the best.
Thank you, sir.
Yeah. Thank you. All the best for the GATE exam.